The Shroud of Turin has been hailed by some as the authentic burial cloth of Jesus Christ, while others have denounced it as a clever medieval fake. In an effort to determine the authenticity of the shroud, a group of scholars and researchers traveled to the Renaissance Cathedral of St. John the Baptist in Turin, Italy, to examine and study the shroud utilizing advanced scientific research techniques. Several of these experts participated in a symposium held at Elizabethtown College, Elizabethtown, Pennsylvania, where they presented their varying viewpoints on the issue of the shroud as an object of archaeological significance. The symposium was jointly sponsored by the Cultural Events Committee of Elizabethtown College and the Marguerite Eyre Wilbur Foundation of Santa Barbara, California. It was organized by Dr. W. Wesley McDonald, Assistant Professor of Political Science at Elizabethtown College. This program is the 6th in the series of 7 presentations on the shroud, videotaped at the Mystery of the Shroud of Turin Symposium, and features Dr. John P. Jackson, a physicist and research scientist at Kamen Science, Colorado Springs, Colorado. He is also past president of the Shroud of Turin Research Project, which performed direct investigations on the shroud.
Very pleased to be here, be invited to speak to you on the Shroud of Turin. I suspect that many of you were here yesterday and heard some of the talks that were presented. One little thing, when I first came here, I got the snow kind of balled us up a little bit, and I was delayed at Pittsburgh, and I couldn't make it all the way to Harrisburg. And lo and behold, I ran into L. Adler, and I said, hey, I don't have my bags. They are somewhere in the airlines. And he said, what's your biggest problem? I said, well, I'm going to have trouble shaving. And so what L. Adler did for me is he gave me Occam's razor. Okay, could I have the first slide, please? We're going to shift gears a little bit here. L spoke to you and others on the chemistry of the image. In other words, looking at the chemical composition of the image without respect to what the discolorations may represent. I'm going to talk to you from a totally different viewpoint, but compatible, and that is, I'm not going to be worried about what the chemistry is, but I'm going to be concerned about what the image structure is. And I'd like to approach it from that point of view. Hopefully between the two, the chemistry and the image analysis, we can get to begin to have some ideas as to what we're dealing with here on the Shroud of Turin. Well, first of all, let's ask the question, why do you see an image at all on the cloth? Well, it's because there are discolorations on the cloth that vary in some way in intensity so that we can recognize that there is a human form represented here on the shroud. Our problem is what caused the image to occur. Well, there are several properties of the image which are worth noting before we get into some of the analyses here. First of all, is well known, if you take the image as it's shown on the shroud and reverse it, interchange the darks and lights, you get this kind of a representation. Now, there's no more information here than there is in the previous slide that I showed you. It's just that this looks more reasonable because this appeals to our psychology more, in the sense that we're used to seeing individuals with white highlights and dark shadows as opposed to dark highlights and white shadows that you see on the first representation. But there's no more information here than there was in the previous slide. Color-wise, the Shroud of Turin image looks like this. It's a yellow-brown type of discoloration for the body image. The blood marks in photographic illumination are clearly red. And this point has been made a number of times that the body image and blood images are different in color. There's also the similarity that the body image looks very much in color in reflected light, like some of the scorches from the 1532 fire. And you can see this by looking at these, say, a flared area here or over here, clearly associated with the fire of 1532. The body image in color at equivalent neutral density points is virtually the same. Now, we have objective measurements that show that this is indeed true, and I'll show you this in a minute. But when I was in Turin, I spent 15 minutes under good photographic illumination studying this area and this area with my eye, trying to see if I could see any difference in color. And I could not see any difference at all in color between those two marks. Now, I don't want you to draw conclusions from that at this particular time. I think Al Adler addressed that very adequately yesterday. I'm trying to give you an indication as to what the color of this image is. Now, in transmission, we've seen this picture before. I'll just briefly reiterate for those who weren't here before that you can learn something when you photograph the shroud with transmitted light as opposed to reflected light. In this representation, we look at it and we say, what do we see or what do we not see? What we don't see is the body image itself. I can kind of see it because I know what I'm looking for, but maybe you can't. You can clearly see the blood marks, though, which have penetrated all the way through the cloth. And the point was made that the reason you cannot see the body image in this representation in transmitted light is because the body image is a surface discoloration of the fibrils comprising the threads making up the cloth. Again, if we go back to the reflected light photograph, for example, look at the face, has about the same neutral density as the flared marks associated with the fire in reflected light. But in transmitted light, you look at those same areas, here's your flared marks, clearly dark, but the body image hardly even shows. The image is a surface discoloration. We need that fact if we're going to analyze some of this image analysis that we'll talk about later. Here's the objective data that I was telling you about. We've measured reflectance versus wavelength or color in Turin. Your red wavelengths would sit off over here. Your bluish wavelengths and ultraviolet sit back over in this region. This particular curve shows the similarity between the body and the 1532 fire scorch areas in color. The other thing that's one can take out of this, now this is relative reflectance, but in absolute reflectance, the body image will vary, and this is at one particular average location, but over all the locations of the body, the tip of the nose to the cloth background varies only about 7% in reflectivity at about the mid-band of your wavelengths here. That's not very much variation, so hence the image on the shroud is very faint, and that's something we have to keep in mind when we talk about these studies. If you want to contrast the body image with the blood, this is a mean blood stain curve, and the two color curves are quite a bit different from one another. Again, the body image is this yellow-brown, the blood images are red. Another way you can see this is by a jet propulsion laboratory enhanced photograph, computer-enhanced photograph, where the colors have been artificially exaggerated. You make the reds redder, blues bluer, greens greener. And I think there's a couple interesting things here. First of all, you can kind of see the similarity between the coloration of the body image and the scorch marks. The color structure going from reds to greens appears to be the same. In fact, it looks so much the same, from my point of view, that it almost looks like all these are of the same color pattern. Now, there are differences between these scorch marks and body image, which you could see in the ultraviolet fluorescence, but in reflected light, there's this similarity of color. And of course, your blood marks, when you do the exaggeration, are quite a bit different in color. And now what we want to do, having given this little preliminary review, and by the way, everything I'm going to say here is published in the Applied Optics Journal, of which Dr. Jumper and Bill Erkeline and I are co-authors. This is June 15th, 1984, Applied Optics. Okay, now what we want to do here is to study what is the image structure of the body image on the Shroud of Turin. Well, to put it a little bit more directly, I think what we're looking for is something like this. We would like to know, and I think it's natural to ask, given that this is an image of a body, is there any correlation between some property associated with the surface of the body and the image intensity that you see on the shroud? That is, if you let x prime, y prime be the coordinates of some point on the shroud, x, y, be the coordinates of the equivalent feature on an assumed body, is there some relationship between a given property and image shading by some kind of a functional relationship like this? Now, this a priori wise, there's no reason why there has to be a correlation, particularly if this is the work of an artist. But nevertheless, I think it's a meaningful question to try to ask, is there a possibility of such a correlation? Well, what kind of examples can we use for a property of a body surface which may be correlated with image intensity? Well, there's a lot, and I'll give you a couple examples. Here's an infrared picture, thermovision image of a statue face. What you may ask is there any correlation, say, with temperature? And that's what you have here. In this, of course, the nose here in this particular case was cold, and the rest of the body was warm, and hence you have this variation. This particular image does indeed have a correlation, a direct one-to-one correlation, I mean the intensities of this, with temperature. That's what a thermovision, infrared thermovision does. So that's a possible candidate. Another candidate will be, let's say, the slope of the body, the gradient of it. Now this is what you've got here, and I think for those of you in the back of the room, this image may look sort of reasonable to you in terms of its shading. Well, there's a good reason for it, because when you look at normal albedo type images, what you're really correlating mostly on is the slope of the body surface. And this can be demonstrated by looking at this contour map, which are contours of elevation, where the contours get close to one another in sort of an average way. And if you squint, if we took this out of focus a little bit, maybe I can do that. Well, I can't do it from here, but if we did take it out of focus, where the contour lines get close together, the intensity will grow. And hence, this would actually be an example of an image where intensity correlates with the slope, the surface gradient of a body surface. But the one that what we wanted to look at first was not temperature, not slope, or electrical conductivity, or perspiration density, or a lot of things that you could correlate. But based upon a study by Paul Vignon in 1902, where he suggested that the intensity of the Shroud image appeared to him to correlate with expected cloth body distances. Now this seemed to me like something that's worthwhile and reasonable to investigate. Okay, so the subject was then, can we find an intensity correlation between those variables? And that's a reasonable question to ask, and it's a scientifically precise question to ask. In fact, what Vignon suggested was, well, take for example the nose. If the shroud covered a body, that would be a part that would be closer to the body, hence you would expect it to be more intense. Parts of the body, maybe the cheeks, eye sockets and so forth, that were further away, appeared to him on the shroud to be less intense. Hence he postulated this correlation. Well, he didn't have any way to check that in his day, but we certainly have the technology to be able to do that. So what we did is take the image on the shroud and run a microdensitometer trace across it. Microdensitometer simply measures light intensity going through your photographic transparency. And you can see that on the shroud there are indeed these variations in intensity. This is a cross-sectional profile across the tip of the nose. Okay, that's the intensity variable. The other variable we wanted to test was cloth body distance. How do you do that? Well, I think the only reasonable way to do it is you go ahead and make a cloth model of the shroud. You make it based upon photographic data to scale. You lay this over a body shape, by the way, this person's alive. You lay this over the person and you adopt a criteria for doing that. One is that all blood marks, which you're going to, of course, assume are blood. Chemistry has to tell you whether that's true or not. But we'll make that assumption. You have to make all the appropriate blood features make contact with the body. Otherwise, you couldn't have had them in the first place if they were blood. Secondly, you have to have all drawn-in features where the cloth would naturally touch relative to your blood requirements, make contact with the appropriate body feature. You don't want, for example, the tip of the nose to be lined up over the right eyeball or something. That would not be right. So you can get a fairly precise and restrictive, unambiguous lay of the cloth by doing something like this. Well, then you can go ahead and measure cloth body distance from that configuration. You can do it photographically and a couple other ways, but we mainly did it photographically. When we did that, we then simply plotted intensity versus corresponding distance, cloth body distance, and for the face, this is the kind of correlation that we were able to achieve. Now, what I have here is a least squares regression line drawn through the data. The coefficient of determination, which is the correlation coefficient squared, turns out to be 0.60. I'll tell you what that means statistically in just a minute. But there is some data scatter across here, and it turns out that actually you want to look at the data this way. I'm going to express it this way. Your standard deviation was about 0.4 centimeters, plus or minus 0.4 centimeters along that line. Now, although there is some data scatter in that particular curve that I showed you, you can nevertheless make some conclusions. And these are just follow mathematically, statistically from the correlation that we got experimentally. First of all, you can reject the null hypothesis. That is, that the true coefficient of determination, the true degree of correlation, remember we're only doing this on a limited number of points, 13 in this case. But if you could do this with an infinite number of points, then the true correlation coefficient squared would be given to you. But you can reject that there's no correlation at the 95% confidence level. The second thing you can do is by looking at where the curve intersects the cloth background, we can say that the correlation will extend to the body surface at a distance of about 3.7 centimeters. So that gives you kind of a correlation range that we're dealing with. Not only can you do this for the face, but you can do it for the entire body. We ran a microdensitometer trace across the body in this particular fashion. Microdensitometer trace is shown up here. Body surface with a cloth draping over it is here. And what you can see is that where the cloth gets close to the body, you start to get intensity. And it seems to be almost universal over the entire cloth. If you plot intensity versus cloth body distance, the correlation looks like this. Intensity versus distance. And this is applied over the entire body surface. It would appear, therefore, that there is a correlation between image intensity and cloth body distance. Anybody can do this who has a photograph of the shroud, is willing to make a cloth model, and is willing to go through the trouble of trying to do the correlation. You'll get similar results like to this. Now, the question is, how good is that correlation? We've done all of these with a limited number of points. What you would like to do is to be able to do it with a large number of points. The problem is in trying to do that correlation is to do it in such a way that you can guarantee registration between points on the cloth and points on the body when you do it. And you got to do it for a lot of points. There's another problem when you have a data scatter like you see. The data scatter does not mean that the correlation is due to an intensity. If there's a correlation mismatch or errors in the image formation process, although that's possible. The other possibilities are that and we have to admit this, that we don't have the body or the cloth, assuming that the cloth covered a body, that would be appropriate for doing the measurements that we just did. We didn't use the real body. We didn't use the real cloth that might have been involved. If you look at variations in how much a body surface can change, well, we've taken a few of these surfaces, and they'll fall within a range like this. This is your nose. There's your lips. And bodies will change a little bit. There'll be errors associated with that ignorance. There are also errors associated with the cloth drape, too. These are on 5 different experiments. And these are profiles taken directly from those. Also, here's the profiles across the nose. for variations of bodies, different noses and cheeks and so forth. And yeah, people's faces do vary. Well, that's no surprise, but here's an attempt to kind of quantify that. So we do have error variation. So we would expect errors in our correlation because of that. But if we want to do large number correlations, we then can use a piece of equipment called a Vp8 Image Analyzer. Now, what all this thing does, it's a hybrid analog digital computer that will take any photograph you want to give it, and it will display it instead of in an intensity space, it will display it in a physical space. It'll convert intensity to vertical relief. Well, that's kind of nice because those happen to be the two quantities that we're trying to correlate here and see if there is a correlation. Let me show you how it works. You'll see a lot of this statue face here, which I'll use in a lot of the control experiments. But look, you've got a monotone image. It's black and white. You see this image for exactly the same reason that you see the shroud. Variations in intensity. Here it is dark and here it is white. Let's take this image and let's put that under the Vp8 and see what it looks like. Now remember, this is just taken with normal reflected light. The Vp8 will show it as this. Now, obviously, the three-dimensional representation here does not correlate with the geometrical structure of that face. Well, there's no reason why it should. That information is not there, and I showed you before that albedo images tend to correlate more with surface slope than they do with the geometrical structure. But look, you've got things like the nose sits here at about the same intensity or relief as the cheeks. Is that any surprising? The nose has the same intensity as the cheeks over here. They also have the same slope. They're flat relative to the viewpoint that you're looking at it with. Now, let's try to see if we can, just as a purpose of demonstration here, construct an image that has distance information encoded into it. And that is possible to do. Now, one way to do it is to take a face, that same face that I just showed you, covered it with phosphorescent paint. The phosphorescent paint, then we can charge optically, and it'll start glowing. So you kind of have a glow-in-the-dark Jesus, I guess, or something. But no pun intended. But it glows in the dark. Then what you do is you take it and you submerge it under a light attenuating liquid. We used food coloring, which has a very uniform attenuation properties. If the surface of the liquid is right up here, then any photons that leave the surface, well, they're going to leave it in all directions, but the ones that you're going to capture with a lens camera up here are the ones that are going to be collimated and come up through the surface. The ones that had to travel further through the light attenuating liquid are going to show up with a lower intensity. Those that had to travel less distance are going to show up with a higher intensity. In short, this little procedure ought to encode an intensity distribution that will correlate with the distance between this surface, the face, and the reference surface of this liquid. Now, what does such an image look like when you do it? It looks like this. This is made from exactly the same face, except no longer do we have an albedo image. What we have is a distance correlated image. The intensity of the nose is brighter than the cheeks and the hair and so forth, because those represent then the relative distance that those features were from the flat reference surface of the liquid. Let's show this to the Vp8. When we do that, we get an image distribution that looks, a relief image that looks like this. We no longer have these funny distortions where you have the nose embedded into the cheeks and so forth. This thing looks geometrically reasonable. It ought to, because we put the information there purposefully. We can also do another thing with the Vp8. Electronically, we can rotate the intensity surface so that we look at the image on its side. We'll take this one, and it looks like that. Here's the profile correlation. Indeed, we have correlated intensity into the image, and the Vp8, the point is the Vp8 can recognize it when it's there. If you want to look at the profile of the face, by the way, and compare it, you can see that indeed we did that. Okay, now let's look at the shroud image. Okay, we're going to take the entire frontal image of the shroud. We're going to subject it to the Vp8, which I've just shown can recognize distance correlation when it is there. The other thing about the Vp8 is that it can look at many, many points all at once, which is its real advantage and its strength. When we do that, this is what the correlation on the shroud looks like. This is the frontal image. That is not a statue. That is an electronic image made by the Vp8 of the intensity distribution on the shroud that gives you the vertical relief. There's no more information here than there is on the shroud image. It's just that it's being displayed differently. That's all that's happened here. The point is that when you look at this, you don't have things like noses embedded into faces and hands embedded or arms embedded into the structure of the body. To a first order, this thing looks like a three-dimensional body surface. And there's only one way that this could have happened. One way. That there has to be a correlation between intensity on the shroud and distance associated with that body. Those two variables have to correlate. And apparently they must correlate pretty well in order to get something like this. Because the Vp8, because of the way it displays information, would graphically show this to us. Any irregularities. You look at the face. Again, you have those intensity variations. You do it with the face, you get this kind of a thing. Now, what you see are, you've got the nose higher than the mustache and lips, higher than the cheeks. The eye sockets are even lower, and so forth. You get something that looks rather reasonable here. Again, you have to conclude, and I don't know any way around this, that there is a correlation between image intensity and distance associated with the structure of that face. You have to realize, too, one other thing. It's called signal to noise. There is noise on this image, but it shows up as roughness. You can see it in the off-image areas. There's variations, small variations, high-frequency variations of intensity, and that, of course, runs right across the image. That's there. You can't do anything about it because it's there. When was this done? It turns out this was done on February 19th, 1976 by Bill Modern at Sandia National Laboratory. After you have, you realize that you can do this, you can convert image intensity to distance, and you've got this quality associated with the shroud image, then you can do other things. One thing you can do is you can take it out of its context on a CRT screen, and you can represent it in terms of some kind of a statue model. Well, we did that by taking microdensitometer traces across the image sequentially all the way down, taking these brightness surfaces, transferring them to corrugated cardboard because that was a rather inexpensive material to use, cut it out, and then stack them in order. When you do that, you get something that looks like this. That was, in fact, our first attempt. And I think by showing this next to the image on the shroud, you can kind of see, I think, what has happened. Just to review. You've got brightness variations on the shroud that by this process have been converted into proportional amounts of relief. Where the image is bright, the image is high, is plotted high in relief. Now, in looking at this, we first of all notice that on small scale, like if you look at, say, around the face area, the three-dimensionality of this looks reasonable, as roughly do the hands and so forth. But the large-scale relationships between, say, the face and the hands and the pectorals don't really seem to be right to us. When we first put it in this form, there wasn't the correspondence between a natural, what you would expect from a human body. Okay, does that mean that the correlation is, there's something wrong with the correlation? Well, we had trouble trying to realize that because how could we, on any and all arbitrary points in a small neighborhood of anywhere, get what looked like a reasonable three-dimensional correlation, but in the large scale you couldn't. So what we thought is, this seemed to be a problem for us. So what we thought was, why don't we try to compute where this three-dimensional surface varies from what you would expect from a real physiologically reasonable body surface. And you can do that. So what we did is this took us about a year or so to do it, but we actually computed by measurements of a real person what you would have to do to this image to bring it to correspondence, general correspondence, with a reasonable body shape. So we did the computation. We had to digitize images. We had to read in the intensities and do the computation. And we would do it this way. You would, in essence, what you're doing is you want to compute a surface such that when you subtract the intensity from it, it will give you a curve that will agree with the general curve that you would expect from a real body shape. This is what that surface finally wound up to looking like. Mathematically, this surface here is how we had to deform the flat background given by the Vp8 to bring the three-dimensional image into correspondence with the body shape. When we use this surface here and we subtract this image from it, we then produce this one. That's all we've done. We didn't take away any kind of extraneous intensities or whatever. I mean, you could first of all see, for example, watermarks. Their water stains have intensity, so they get plotted. Looks a little strange in one sense because the shoulders are gone, but remember that information was burned away in the 1532 fire. Here's another watermark here. It shows up over here. We didn't take any of that away. All we did is just do the modification or the computer calculation that I just told you. And you can compare this now with a body shape. Here's the shroud. Here's the body surface. You can see how relatively stiff this looks like in general relative to this. When we do the correction, this is what we wind up with. Now, I'm not saying we've got this thing perfect, but I think you can kind of see what the general trend is here. The interesting result here is, and I'll show this to you in a minute, is that the mathematical surface that we had to use in order to correct, shall we say, or to deform the Vp8 image into a reasonable body surface looks very much like the way a cloth would drape over that body surface. And I'll show you this in just a few minutes. But I'd like to address for the moment, take an excursion here to address one point that was raised by Joe Nickel yesterday. He argued that, or said that this process is based upon circular reasoning. I think that's a good point to raise. It's a valid point to raise, and it is something that needs to be addressed. And I'd like to address it at this moment, at this point in time. The answer is that, or let me just digress a minute. The reason you would say that this is based upon circular reasoning is something like this. If you're going to conclude that a cloth, the image on the shroud, is consistent with a cloth draping over a body, the circular reasoning that he's alluding to is that, well, you've assumed a cloth drapes over a body, and therefore you come up with the conclusion that a cloth draped over a body. You know, that's pretty circular. But the problem with that is that to say that there's a circular argument here, you have to look at what the information is that's available. You've got a cloth surface, you've got a body surface, and you've got an intensity distribution. The two variables that we played around with here are cloth, drape, and generating surface. I mean, receiving surface and receiving surface and generating surface. The thing that we cannot play with is the intensity distribution. That is a given to us. We don't have the freedom of changing that. If we did have the freedom of changing that, then I would agree the whole thing would be circular. But we have to, when we do these correlations, we're doing it relative to a given intensity distribution. Because we can do that, we're doing that to something that is given to us, it cannot be circular. Let me demonstrate this by an experiment. Let's go back to our face under a light attenuating liquid where we generate an intensity distribution. Suppose instead of using a flat reference surface, instead of that, let's suppose I use a curved surface, let's say to simulate a cloth, something close to it. Okay? We'll keep everything the same. We'll use the same liquid here and so forth. Well, clearly, because of the difference in the receiving surface here, or the reference surface curved here and flat here, the resulting intensity distribution is going to be different. Okay? It's going to be different. The point is that on the shroud, the intensity distribution is given to us. We don't have that choice. So if we were indeed given an intensity distribution that looks like this, and if I tried to take this surface here and this face here, take these two surfaces, choose those, I could indeed get a one-to-one correlation between intensity and cloth body distance. I think it's obvious. But what if I would have tried to do the correlation with, instead of this surface, I try to do it using a flat surface? There's no way I could have gotten an intensity correlation to agree. Vice versa. If I was given an intensity distribution that looked like this, with a flat reference surface, I can obviously, in this case, do the correlation. But if I tried to use this kind of a surface, I could not make the one-to-one correlation. Okay? So the point is that because the intensity distribution is given to us, the argument is inherently non-circular. The second question is, can the Vp8 recognize these differences? Okay, so I've already shown you one image where we made a distance encoded image relative to a flat surface. Now let's do it relative to a curved surface. This was a plexiglass container that was deformed to model what a cloth might look like from some previous data that we had. Filled it with a light attenuating liquid, put the glowing face in here, and then photographed from below the picture. When we do that, this is the way the brightness distribution looks like. This is still the same face. The intensity distributions now have been rearranged. It's different than what we had before. In essence, for example, the nose is almost nearly the same intensity, not quite, but nearly the same intensity as the cheeks, whereas in the other one, it was not. The Vp8 looks at this, and this is the kind of image you'll get. It sort of has a concave appearance to it because of that, because the curved reference, the reference surface is now curved instead of flat. The previous one, the one that was done relative to a flat surface, the Vp8 looks like that. Clearly, the two are different. Therefore, the Vp8 can recognize differences associated with intensity, which might be correlated with cloth drape, relative as we've described. Okay, what are we saying here? Have we proven that the Shroud of Turin therefore must have covered a body shape, a three-dimensional body shape, when the image was generated? No. Rigorously speaking, no, we have not. And we do not claim that we have. What do we claim then? We say, okay, that if you take this image right here, try to fill in the arms, by the way, with your eyes, but I can't provide that information to you because it's not there. It was burned away in the 1532 fire. But this is the computer-corrected image relative to that reference surface, which I'll show you in just a minute. The point is, what we're claiming is this. If you take this body surface, and this does correlate, agree, it's a physiologically reasonable body surface. You take this body surface with all of its structure, everything, you can, with one single global mapping function, one single relationship that applies all over the body, relative to this surface, compute exactly the image intensities on the shroud as you would measure them with a microdensitometer everywhere. That's what we are saying. That is a fact. That is a mathematically rigorous conclusion. We can do that. Now, the fact that you can start with something that is physiologically reasonable as a body surface, and you can use, and you have to use a surface that looks like this to do it. And the fact that that surface looks like the way a cloth drapes over a body, in fact, that's draping over that statue I just showed you. The fact that those two appear to agree very well argues that the image intensity on the Shroud of Turin is correlated, it is self-consistent with the idea that you have a body, a full three-dimensional body under a cloth that is draping over it, not flat, but draping over it, and you can correlate all this with a single global mapping function. Now I'm going to use Occam's razor here that L. Adler gave me. Occam's razor, you want to look, science likes to lock onto simple explanations. Realize what we've done here. You've taken a complex body surface, a rather complex cloth-like surface, and you've taken one single mathematical function, and you can correlate and derive the entire shroud image from it. And I think that, no, we haven't proven that, but I think that they're cloth draped over a body, but I think the self-consistency here and the elegance of having such a simple relationship, I think one has to be at least impressed by that kind of a relationship and image structure on the Shroud of Turin. Okay, the minute you say that, well, you can do this with a cloth drape surface like this, then you have to begin to ask questions like, well, what about geometrical distortions in the image? Now, this is an independent question, really, from what we just addressed. We were talking about intensity being this cloth drape, if you will, being encoded into the intensity distributions of the shroud image. I'm asking a related but really independent question. What about the two-dimensional positioning of image features over the cloth? What about those? If there was a cloth over the body, you would expect there to be distortions in the image. Like if the cloth is over here, then we're opening the cloth up and looking at it. There's got to be a distortion. There ought to be distortions in it if this was in fact the case. Well, here's an example. This is an infrared thermovision picture of a cloth over a hot statue. Okay, in fact, it's that face I just showed you, but it's been heated. You put a cloth onto it. The thermal penetration will cause an image to form on the reverse side of the cloth, and we see this with an infrared camera. If you then take the cloth and open it up so it's flat, you then get distortions in the image distribution. Well, that's what I'm talking about, lateral distortions. I'm not talking about the intensities now. I'm talking about lateral distortions. Another way to sort of talk about that is to consider a healthy human being, and we'll look at him, take a picture. What I did, I just want to get an idea what kind of magnitude of cloth distortions you might expect. We had cloth drape data from previous work, so you can kind of see it here. I cut out a surface representing that cloth in miniature. This is about half scale. Then I took a cloth and using double sticky tape, I affixed the cloth to this mold that I made. Then I took that image that I just showed you, projected it right into the cloth, and then sketched that image in to the cloth. Then I could pull the cloth off and then flatten it out and look at it, sort of simulating what you might expect if the cloth covered a body. And this is what I would get. This is the body surface I just showed you, and these are the distortions that you might expect. There are two. One is an elongation, a slight elongation in the image. But because the cloth tends to drape more this way than it does this way, and it's distorted that way, you would expect more distortions laterally than you do longitudinally, and that's in fact what you see. You get broadenings of the hip and so forth. Well, now when you look at the shroud image, the question is, are such things there? Well, there are a number of authors who have speculated, who have noted that, for example, the fingers might appear to be too long, or the arms might be too long, and they give different reasons why this may be so, all the way from an artist trying to contort his image for reasons of modesty to put the hands over the proper location, to Marfan syndrome, and other explanations for why this might be so. Well, rather than be subjective about this, we took a series of 80 volunteer cadets at the Air Force Academy who volunteered on their own time to do a little experiment. We selected them to give roughly the right height range as indicated on the shroud. It's about 5'10" plus or minus about 2 inches was our criteria. 5'10" fits it pretty nicely. By the time you're getting up there at 6 foot or 5'8", image features just don't coincide. Then we photographed them and we constructed our own statistical ensemble. We put them in the indicated image on the shroud, and we measured different distances over the entire ensemble. Then we would take these measurements and compare them with the image on the shroud when the shroud, of course, is laid flat. And what we found are a number of data points which will be published in the future. But I'll tell you what one was that I think it's sufficient, but it's significant here. And that is the length of this arm right here. That turns out to be over 2 standard deviations too long from our ensemble that you have. There is an elongation there. Now I kind of have monkey arms myself. I'm 6 foot. I'm actually too tall. But I'm a 35-inch sleeve. But I'll put my arm against this on a full-size picture, and I'll put my fingertips right there, and my elbow will come right about over here. Right about in here. There is an elongation there. That is a geometrical distortion, and it's not explainable by cloth stretching. It's not explainable by photographic distortion. I can explain that later if you want to ask me why that's true. And it's not explainable by physiological variation. I believe that's an objective number, and there are others, that tell us that image is distorted. There are such distortions in this image. Also, the hips appear to be too wide, and probably the hair looks like it's pushed away from the face, and that's another one. We talk about cloth body distance here. Cloth body distance is not really a well-defined quantity if you try to define it with one number. Distance is a vector, not a scalar. In other words, distance has a magnitude and a direction to it. When we say that we're correlating distance, you really got to specify not only the magnitude of the distance, but its directionality as well. So a reasonable question then arises, well, what would be the directionality of points of mapping points on a body to points on corresponding points on the cloth as indicated as to where the image is located? Of course, you were making the assumption that a cloth covered a body, but under that assumption, what is the direction of the mapping between points on body and points on cloth? And by the way, that mapping has to be essentially one-to-one because the image is fairly highly resolved. So it is a meaningful question to ask. Well, what I did was to take a microdensitometer trace of the shroud image. This is right across the nose. Then we took our experiments. This is a real human face and a real cloth draping over that human face. Now, if we take the points right here where the nose intersects the cheek, it's right here, and let's just project that down, and then we have to make the distance across here equal to the distance along this way, obviously because you're doing this along the cloth. Then ask, where are these image features lining up on the shroud, on a real body? And the answer is they line up more or less along a vertical mapping. See, there are other kind of mappings you can get. You could hypothesize, well, maybe you're mapping normal to the body, normal to the cloth. But what it looks like from this is that you're mapping essentially vertical. Here's another one. Do it at the level of the knees. Here's a microdensitometer trace. And here are real knees. Aren't they gorgeous? From a volunteer with a cloth over it. Again, you do the same kind of a thing, and the mappings more or less agree with a vertical mapping. They don't really agree with a perpendicular to the cloth or body. Otherwise, you'd see the image of this knee probably way over here, but you don't, according to the microdensitometer. So the real question becomes then, if the body covered, or cloth covered a body, what is the directionality of your mapping that you have to use in this, when you talk about these distance correlations? I think that the mapping, or the best one that we have, looks like it's vertical. The body's laying in a horizontal position, vertical upwards. Now, that's kind of interesting, because that is consistent with other things that we have. For example, there are no side images on the body. That would be consistent with a vertical mapping. Now, we can't prove that because there are other ways that you could explain that as well. However, well, I'll get to that in just a second. The other thing that I think is interesting, a vertical mapping would explain some other things. I've always been kind of intrigued with right here, that where the top hand overlaps the bottom hand, there's a region of blanking right in here. There's also some blanking right around in this area, and probably up in here. But I'm right now interested right in here. There's a blanking. Why would just the simple presence of the top hand prevent an image for a small distance from occurring on the bottom hand? Well, I think if we're talking in terms of a vertical mapping, we may have a self-consistent relationship here. And you also have to realize, accept that there is this distance correlation in the intensity of the image. Now, if the distance correlation goes over 3.7 centimeters, as those measurements that I showed you before indicated, then clearly, over this short distance, the cloth could not have been that further than 3.7 centimeters away from the cloth, from the body. Yet there's no image here. But it's backwards, but it shouldn't make any difference. Here's the thighs, and this is the top of the hand. Now, if the cloth, instead of going out like it did over here, would have gone down right next to the side of the top hand, where the cloth goes vertical, there would be no image because of this vertical mapping. Then when you open the cloth up, then you have this this vacancy in the intensity of the image. And really, the width of this thing is about the width of a finger. So I think that's self-consistent. Now, the other thing I said was there are no side images over here. Well, you could always argue, well, the cloth was not in contact with the body. That would certainly explain it. You may have something around it. There are a lot of other ways to explain it. However, I think the very fascinating thing is taken from Gil Lavoie's observation, where he talked about the side blood that runs right off the image, and he explained that as blood coming down a forearm, wrapping around the body, pooling on the back. He argued that in order to get that contact, that blood contact, to make this, that the cloth must have been in close proximity, at least, very close to the side of the body to do that, yet there was no side image formed there. There's an argument, I think, that is consistent with this idea of a vertical mapping, but and would argue against the idea that the cloth was held away or that something was in between the cloth and the body, preventing this an image from being formed. Again, assuming a cloth covered a body. Now, I'm not prepared to say what I think would cause a vertical mapping at this point. All I'm trying to do is to give you the mathematical characteristics of the image as I see it. I'd like to talk about one mechanism here. What's of interest here would be the artist mechanism. We should not underestimate the ability of the human mind and hand to create works of art that are astounding. Here is one such beautiful example, dating from hundreds of years ago, the Pietà. In the context of the Shroud, we have an image. And I think there are three questions that I think are relevant to the artist hypothesis. I think the first one is such an intensity distribution technically executable by an artist? Secondly, is it reasonable for a medieval artist or before to have thought in terms of an intensity distribution, an intensity image, a distance correlated image, rather than, say, an albedo image? And third, are there any examples of an image that was put on cloth that has distance correlation? Now, by the way, we can't use the Shroud as an example of one such image because the Shroud can't be both hypothesis and supporting data at the same time. Now, that's circular reasoning. To address the first question of whether it's executable, and let me just remark that this is a meaningful question because the intensity distribution of the Shroud, as I showed you first, was only like about 7%. That's very faint. And that raises an automatic question: can the human eye and hand execute distance correlations over that limited range? And I think that's a reasonable question to ask. So what I did is I used the old statue here, face, as the generating surface. And I'll consider an artist as an image formation mechanism. He starts with some previously experienced body shape data, and then he's going to convert that into intensity. What I did was I located two forensic artists, certified forensic artists on the police force, in two different police forces. I chose them because they have to provide realism regularly in their professions, and they work in monotone shadings similar to what you have on the Shroud. This is the kind of artwork that at least one of the artists is capable of doing. Just to give you an example of the quality of the individuals that we had, I used. Now I only used two, but probably we should be using some more. But just to give us an initial benchmark here was my thinking. What I had them do was to take that body surface, this statue, and I asked them to shade with pencil onto paper the intensity distribution of the face, of that three-dimensional face. I even let them measure it. I told them exactly what this three-dimensional correlation is. I briefed them on it. But what I didn't do was to give them Vp8 results to help guide them in making their images. That would be unfair. I also restricted their range, their dynamic range of operation, to the 7%. I also permitted them to do erasure. I'm not sure how you would do that on the case of the Shroud, but I allowed them to do that to try to get as close as we could. And I'd like to show you what some of those results were. This is one. I have to boost the contrast up so you can see it. But this was one image that the artist made. Now, that sure is a far cry from what the kind of quality we saw before, but remember, we are restricting his dynamic range of operation. You look at that with the Vp8, and that was his result. Here's the second one. This is a different artist. And that's his result. Now, I wanted to understand what was going on here. So then I did an experiment where I said, okay, now I'm going to do two things for you. I'm going to give you a distance encoded image. I'll do the distance encodement for you. So I gave them a black and white photograph, distance encoded as I've told you before. Then I asked them, go ahead and copy this thing. Just copy it. And I'll restrict the entire dynamic range to black to white and see what they can do. And I think everybody would agree that would give overwhelming advantage to an artist, more than what would probably be reasonable to expect for a shroud. Can we turn down the light, please? There's going to be a couple in here that'll be pretty dark, and just leave it off for the moment. This is one that the artist had. I think that from what we saw before, there is an improvement here. And my personal feeling is I think we're seeing a correlation that starts to be comparable to what you see on the shroud in this particular one, although there are some differences here. Clearly better than what you saw when you had the restricted dynamic range. But please remember, they had the whole full range of black and white to use. They had the erasure mechanism. And I gave them the distance encoded photograph to copy, too. The second artist, this was his result. I think what's also interesting is here we have two different artists, but the two images are still different from one another. There's a stochasticity associated with this as well. I think that the faintness of the image is something that is something that needs to be reconciled. I mean, you have to consider when you're considering the artist hypothesis, because that really does seem to truly restrict the ability of the eye-hand-brain system from putting an image onto cloth. Now, the second question, is it reasonable that an artist would have thought in terms of a distance encodement? Well, there are examples of where an artist tried to put an image of a body or face on cloth. It's either in trying to copy the image on the Shroud of Turin, or it's trying to make a so-called Veronica's veil. Every example that I've seen, and I certainly don't profess to be an art expert or art historian, but the ones that I've seen all have this kind of a character. They look like they're albedo images. The artist tends to tries to put them on as though the cloth were reflecting the image of a face, rather than trying to think in an abstract way of how a cloth might be discolored by some mechanism that might have caused an image. That's one. Here's another one, again, clearly trying to get an albedo type of image. Intensity of nose, like the intensity of the cheeks. These are all on cloth. I mean, you can see the cloth right down here. Here's another one. No tendency to try to think in terms of putting in a distance encoded image like we see on the Shroud on. By the way, the Vp8 of this one looks like this. Now you kind of see for yourself. Here's one on the Shroud of Turin that somebody tried to make. And interestingly, what they try to put here is a reflected image, an albedo image, not a distance encoded image. This one, by the way, was done before the fire of 1532 because there's no fire marks on it. Okay, now the other question, the last question for an artist is, hypothesis, is there any example, surviving example of a distance encoded image? I don't think it's reasonable that an artist would have thought, although I admit he would have the intelligence to do so, I think it's improbable, based upon the historic record, that he would have thought of it. Here's a few more examples. These are various images. I'll just give you an anthology of these really quick, and then that'll conclude my presentation. There's an example of an artist's attempt to try to copy the Shroud. It's not very good. If you want to ask how good was he trying to be, well, you can kind of get an idea from looking at how good he tries to paint these individuals. Here's another one. They seem to have trouble with this putting a black image on a black on top of a black. I'll show you two that predate 1532 fire. There's a Vp8. Keep in mind what the shroud looks like, Vp8. Those are two, and it looks very flat, very plateau-like. This is a post-date 1532. You can see that because here are the fire marks that are showing up in the Vp8 imagery. You can look at the face up here and how the face is really sort of mashed in. Here's another one, post-date 1532. You see the fire marks. See how the face is, again, mashed in here. There's the shroud. Here are a few icons, paintings that have been done in the past centuries of Christ. All of them are albedo images. No example that I know of a distance encoded image. Here's some Vp8s of those. This is the Vp8 of this one. Then I'll just sort of flip through these. These are all Vp8s. That's the hair, by the way. It's black, so it doesn't have intensity. That was, again, an albedo image. Here's a Vp8 of it. In summary, I think we have a self-consistent, we've demonstrated a self-consistent relationship between image intensity and cloth body distance. We do not claim to have proven that the cloth draped over the body, but we have demonstrated a self-consistency with that hypothesis. And I think a very straightforward and rather elegant way to do it, elegant in a scientific sense. We've looked at a variety of hypotheses that might explain this distance correlation, and that's really what you have to do. I've shown you my thinking on the artist hypothesis. There are others. I think the best mechanism that we've come up with is it's a bas relief that you heat, and you use thermal diffusion to create an image. That was the best Vp8 that we were able to generate. That is not the same as Mr. Nichols' mechanism, which also uses a bas relief. But that was the best that we could come up with. However, that does not have the two-dimensional distortions in it, and it also puts an image through the cloth on the reverse side. We do not have a self-consistent explanation for the image on the shroud. I think right now, where are we in shroud studies? I think I like to compare that with Kepler's laws. Kepler had three laws that he formulated from astronomical data. The first was that planets go around the sun in an ellipse. The second one was that the radius vector of the planet, with the sun at its focus, sweeps out equal areas and equal times. And the third is that the square of the period, of the orbital period, is proportional to the cube of the perihelion. That's the closest approach of the planet. Well, he had three laws. And those three laws mathematically represented the scientific understanding at the time of planetary motion. What was needed was a Sir Isaac Newton to come along and with one simple, elegant theory, namely his inverse distance squared law of gravitation, explain all of this data, and which is derivable from it. I tend to think that we've advanced to the stage of Kepler's three laws. I think we basically understand, at least in a first order sense, I think we understand the chemistry of the body image. I think we understand the image structure. Chemistry is the first law. I think that we understand the distance or the image structure of the shroud image, at least in the terms that I've expressed, both in terms of distance correlation and directionality. And I think what we need, what's needed now is a Sir Isaac Newton to come from somewhere and put all this together for us. So my final remark is, Sir Isaac Newton, where are you? Thank you.
The Mystery of the Shroud of Turin, with Dr. John P. Jackson, is number 6 in the series of 7 presentations videotaped at Elizabethtown College, Elizabethtown, Pennsylvania, where a panel of 8 scholars and researchers were brought together to present their views on the authenticity of the Shroud of Turin. The symposium was jointly sponsored by the Cultural Events Committee of Elizabethtown College and the Marguerite Eyre Wilbur Foundation of Santa Barbara, California. It was organized by Dr. W. Wesley McDonald, Assistant Professor of Political Science at Elizabethtown College. Information on the additional videotapes in the Mystery of the Shroud of Turin series may be obtained by writing to Action Video Productions, 1828 State Street, East Petersburg, Pennsylvania, 17520, or phone area code 717-560-0605. The Mystery of the Shroud of Turin programs were produced by Action Video Productions, East Petersburg, Pennsylvania.